Okay, we're going to do number 55 in chapter 6. And this is what it says. You're driving along at 25 meters per second with your aunt's valuable antiques in the back of your pickup truck. Alright, so you're driving along. Here's your pickup truck. Kind of an old school pickup truck. And you got this valuable vase in the back of your pickup. Worth lots of money. Alright, you're driving along like this. Okay? And you're driving at 25 meters per second. So we have the initial velocity. Your initial velocity this way is 25 meters per second. Okay, so we're getting this set up. You suddenly see a giant hole in the road 55 meters ahead of you. So in front of you, 55 meters, is a giant hole in the ground. If you drive into that, you're going to destroy your truck and the antiques. Fortunately, your foot is right beside the brake and your reaction time is 0. Can you stop the truck before it falls into the hole? Okay. And the question, part B, is if your answer to part A is yes, can you stop without the antique sliding and being damaged? All right. We have to look up on table 6.1. In the book, it tells you different coefficients of friction. In this case, our coefficient of friction is rubber on concrete, essentially the rubber from the tires on the concrete, and it's equal to 0.8 for kinetic. And for static friction, it's equal to 1.0. Alright, so what's your car usually using, static or kinetic? Well, normally when you're braking your car, it's static friction. Your tires are not skidding, you're just slowing down the rotation of the tires. Kinetic friction occurs if you lock up the tires, if you hit the brake so hard that the tires stop moving and you're just skidding across the road. That would be kinetic. Nowadays, most cars, within the last 20 years or so, have anti-brake systems, automatic braking systems, so that you are always using this. So even though you slam on the brake, your brake doesn't actually lock up the tires, it just pumps the brakes so fast, that faster than humans can do it, that it keeps the brakes from locking up and it allows you to stay up here, which allows you to stop faster. So brakes are way better now than they used to be. Yeah. Alright, so the question is, can we stop in time before we get to the hole? Well, that's a good question. What is our deceleration? That's what's going to determine it. Well, we're going to do this like everyone. We're going to do a free body diagram on the truck. So we got gravity, we got normal force, and we got friction. Okay? Now let's do the worst case scenario first. Let's say it's kinetic friction. Let's say we just hit the brakes and we're skidding because our truck's really old. Okay? Then I'm just going to do, they're all on the axes, so I don't have to worry about step 2. This is my y-axis going up here. This is the x-axis going this way. So step 2, I don't have to worry about components, they're all on there. So I'm going to do F net x is equal to kinetic friction. But I'm accelerating, so this becomes ma, and this is negative, sorry it's going that way. Ma is equal to minus mu sub k times the normal force. Well, what's the normal force? Well, if I do F net y, I get that the normal force minus mg has to be equal to 0 because I'm not flying off the road, or the normal force is equal to mg. So I can plug that in there. I get ma is equal to minus mu sub k times mg. Notice the mass goes away. It doesn't matter what the mass of the truck is. The maximum acceleration I can do is mu sub k times g. Okay? So now if I do it for static friction or kinetic friction, it's going to give me a different value here. So let's do, for kinetic friction, we're going to do 0.8. So A, this becomes minus 0.8 times 9.8. And we get our acceleration is equal to minus 7.84 meters per second squared. All right, so if I slam on the brakes and I skid, am I going to stop in time? Well, we know our acceleration, we know the distance, and we know our initial velocity. So now it becomes a constant acceleration equation. We're going to use this one again. This is 0 over here, right? The final velocity is 0. What we want to figure out is how long it takes us to stop. If that's less than 55, we're okay. So I'm going to solve this for x. I'm going to get x is equal to negative v naught squared over 2a. Or negative, I'm going 25 squared over 2 times negative 7.84. And when I do that, I get the distance is 39.8 meters. And guess what? Yes, I can stop before the hole. But that's only part of the question. So that was part A. So the answer is yes, you can stop in time. This is all part A. In part B, they ask, can we save the vase? Now, how are we going to save the vase? Well, they give us the coefficient of friction between the vase and the back of the truck. So the vase is sitting in the back of the truck. So this is part B here. So the static coefficient is 0.60 between the vase and the truck. Kinetic is 0.3, but that doesn't matter, kinetic, because once it starts to move, right, if you go past static, once it moves, it's gone, it's broken. So we're only going to worry about the static friction. We have to see if we can make it using static friction. So I'm going to do a free body diagram on the vase. Okay? So we have the mass of the vase times gravity. We have the normal force here. Okay? And what's happening? The whole thing is accelerating, right? Which way? Well, it's actually accelerating that way. So its inertia is going this way. So what we have to do is figure out what's keeping it from moving. So think of it this way. When I slam on the brakes, which way is the vase going to try to move? So if I slam on the vase, slam on the brakes, the vase is going to try to move that way because it has its inertia, it's moving that way. So friction's going this way. So we have static friction on the vase, and if that static friction is greater than our acceleration, then the vase will survive. So I'm going to do F net x is just equal to negative Fs, or, and this is going to be ma, right? So ma is going to be minus mu sub s times the normal force. The normal force is equal to mg, because n minus mg is equal to this. This is 0, so the normal force is equal to mg. So again, I get ma is equal to minus mu sub s times mg. And the acceleration that the vase can handle is minus mu sub s times g. And we know the acceleration is 0.60 times 9.8. So the maximum acceleration that the vase can handle is going to be 0.6 times 9.8, 5.88. Okay? If you try to accelerate any more than that, meaning you hit the brakes faster, so if you hit the brakes to try to do this amount, the vase will be destroyed. But if you only decelerate at that amount, the vase will survive. So the question is, well, if I'm really a talented driver, I don't slam on my brakes, I just slow down using the brakes so that I maximize it at this amount, will I still stop in time for the hole? So now we're going to plug that back into here and say, oh, okay, we're going to use the same equation here so that we solve for x. This is 0 over here. And so x is, again, this is 0 too. X is going to be equal to negative v naught squared over 2 times a, or x is going to be equal to negative 25 squared over 2 times negative 5.88. And when you get that, when you do that, you get that the distance is equal to 53.15 meters. So yes, you have 55 meters. So if you were really skilled, you didn't slam on the brakes, but you pushed the brakes down at just the right amount so that you kept it at exactly this value, you didn't go over that, you would stop in just under 54 meters, you'd have 1 meter to spare and you would save the base. Now you gotta be a really good driver. But yes, you can.